Okay, so in the last video, we learned about the frequency response for RLC circuits, and the frequency response tells you how a circuit is changing the input to create the output. Okay, so it tells you how the amplitude changes and how the phase changes for an input sinusoid at a particular frequency. And so you could imagine if that RLC circuit is maybe making some amplitudes of some frequencies get smaller and other amplitudes of other frequencies get larger, then that circuit is really acting as what we might call a filter. Okay, it's going to filter different frequencies out of the input and maybe even change others in particular ways. Okay, so today we're going to talk about some examples of filters, and you might have seen some of these before. Okay, so filter examples. So this entire video is just going to be examples to help you get used to frequency response and some operations with complex numbers and things like that. And these examples will be useful, for just general examples of these types of filters and things that you can maybe build off of to make more complicated filters. So the first one is going to be a low pass filter. Okay, which we usually denote LPF, low pass filter. Okay, so what is the idea behind this filter? Well, it really says what it does. Okay, it's going to pass the low frequencies, meaning if you put in a sinusoid with an omega value that's relatively low, right? So, close to zero, then this filter is going to let those frequencies through. It's not going to reduce the amplitude as much for those frequencies, and it's going to reject, or sometimes we say attenuate, the high frequencies. So for inputs where omega is large, this filter is going to reduce the amplitude of those, okay, maybe even bring it very close to zero. Okay, so this is a low pass filter, and you'll see when I start plotting some things, you'll see exactly what I mean. But generally, we want to pass the low frequencies and reject the high frequencies. Okay, so these types of filters, one application is in the music industry. They can apply these filters to different sounds that are recorded, okay, to try and change the sound in some desirable artistic way. Okay, so you can imagine if you're recording maybe a kick drum on a drum set, it's a very low frequency sound, you might want to put some sort of low pass filter on it so that you can get rid of any like noise in the high frequency ranges that you don't want on your sound. Okay, but there are many applications. And today we're just going to look at a very simple one. Okay, so I'm going to draw a filter here. I draw a circuit. It's going to be very simple. Okay, so I'm going to have my input be, I'm just going to draw it like this. My input is some voltage source on the left. Okay. And my output is going to be the voltage across this capacitor. Okay, and this resistor, I'll have a resistance of R, and the capacitor, I'll have a capacitance of C. And don't get the idea that this is the only way to make a low pass filter. There are many, many, many ways to make low pass filters, and they can get much more complicated than this, depending on the exact frequencies that you want to change using this filter. But we're just going to keep it simple and look at a very simple filter today. Okay, so how can we go about analyzing this filter? Well, we want to know how this filter affects different frequencies. What did we learn that tells us about that? Well, that's the frequency response. Okay, the frequency response tells us how a filter changes input sinusoids at different frequencies. Okay, so how do we look at the frequency response? Well, remember the frequency response, just to remind you, I'll erase this in a second. Okay, it's the output phasor divided by the input phasor. So that's what we have to find. We want to find the output phasor divided by the input phasor. Okay, we want to find that relationship. So how do we do that? Well, we got to phasorize. So I'm going to phasorize. And what do we get? Well, we get our phasorized version of our resistor. The impedance of the resistor is just R. Capacitor impedance is 1 over j omega c. Our input phasor is V sub I, and our output phasor is V sub O. Okay, so that's our general phasorized picture. Okay, and now we want to get the output phasor in terms of the input phasor. Well, it looks like a voltage divider, right? We saw this actually in a previous video. How would I get the relationship between the output phasor and the input phasor? Well, by the voltage divider, it's the input phasor times this impedance divided by the sum of these impedances. Right, so VO is going to be VI times this impedance divided by the sum. Okay, so I'm going to write use a voltage divider. Okay, and this is, in phasors, obviously. Okay, like using the impedances in the phasorized domain. And we want to get the frequency response H of omega, which we said before is the ratio of the output phasor to the input phasor. We just said the output phasor is the input phasor times this divided by this. So when I divide by this input phasor, I'm just left with the rest of it. So this divided by this. Right? If V out is VI times whatever, then when I divide by VI, I just get that whatever, right? Which was this impedance divided by the sum. Okay, so that is our frequency response. That's already it. Okay, that's already it. But what we want to understand is how this frequency response is really affecting the magnitudes in particular of the inputs and outputs to the circuit, because we want to see, are the magnitudes of the low frequencies kind of let through, and are the magnitudes of the high frequencies kind of rejected or attenuated? So we want to look at the magnitude of H of omega. And this is not in the best form for us to understand that. Okay, so I'm going to multiply top and bottom by j omega c just to get rid of the 1 over j omega c. What do I get? I get 1 over, and then this times this gives me 1, plus that times r, which is j omega rc. Okay, so that is my frequency response. Now it's in a nice form, because now it's relatively easy to get the magnitude of it. How do I get the magnitude of the ratio of two complex numbers? One is a real number, but that's also a complex number. Well, this was, gone over in the complex numbers review video. The magnitude of the ratio of two complex numbers is just the ratio of their magnitude. So the magnitude of the top is 1, divided by the magnitude of the bottom is the square root of the real part squared, which is 1 squared, plus the imaginary part squared. So RC omega squared. Let me write this a little bigger. RC omega squared. Okay, so that is the magnitude of the frequency response. And while we're at it, let's just for practice, let's find the phase too. We really just need to look at the magnitude if we want to understand the low pass characteristics, but the phase is important as well. So how do I get the angle of the frequency response? Well, again, how do I get the angle of the ratio of two complex numbers? Well, again, from the complex numbers video, it's just the angle of the top minus the angle of the bottom. Okay, so definitely review that if that sounds unfamiliar. So it's going to be the angle of 1 minus the angle of the bottom, which is 1 plus j omega rc. Okay, what is the angle of 1? Let's think about it. Here's my complex plane, real and imaginary. 1 is right there. What is the angle that that complex number makes with the real axis? Well, it just makes an angle of 0. Okay, so that's just 0. This is 0. So I'm not going to write it. And so I get negative this angle. Okay, well, where's that complex number? That complex number has real part 1. And the imaginary part, I don't know where it is, but it's somewhere on this line, right? For different omegas, it could be anywhere on that vertical line. But all those complex numbers are in the first or fourth quadrants. They have real part that's positive. And as we said in the previous complex number review video, you can see I'm referencing that a lot. The magnitude, the angle of any complex number whose real part is positive is just the inverse tangent of the imaginary part divided by the real part. So we get negative from that negative, inverse tangent of the imaginary part divided by the real part, but that's just 1. So just omega RC. Okay. So let's try and plot both of these. And then you'll see where the phrase low pass comes from. Okay, so first I'm going to plot the magnitude of the frequency response. So it's this, and we don't care about it being exact. We just want to get a general feel for what's happening. Okay, so let's just think about when omega is small versus when omega is big. When omega is small, let's just say when omega is 0, this whole term goes away. I just get 1 over 1. So I know that my function equals 1 when omega is 0. What about when omega is really large? Well, whether omega is large and positive or large and negative doesn't really matter, because when I square it, I get the same thing. In other words, we can see this function is actually even, okay, even in amplitude, okay, which actually we're going to prove in more generality, I think, in the next video. Okay, so this function is even in amplitude, meaning whether I plug in omega or negative omega, I get the same function. That's what it means to be even. Just I can, if I plug in this value or this value, I get the same thing. In other words, it's symmetric about the vertical axis. That's what even means. Like cosine is even. So this function's even in magnitude. Okay, so whether I plug in really large positive omega or that same omega negative, I'll get the same thing. So if that omega is large, then this term is going to be really big. So I have 1 over something really big, that's going to go to 0. So I know that eventually this function is going to get really small. And what happens in between? Well, it kind of looks like 1 over sort of like, 1 over, I mean, it's 1 plus omega squared-ish. Anyway, you can plot this on any of your favorite plotters. It turns out it looks something like that. Just a ballpark. Okay, just a ballpark estimate. Let me draw it a little better, maybe something like that. It doesn't have to be exact. Okay, so why is this telling us that this is a low pass filter? Well, where are the low frequencies in this diagram? Well, the low frequencies are when omega is small, either positive or negative and small. So I would say the low frequencies are somewhere around here. And the high frequencies are sort of in either of these ranges when the magnitude of omega is big. Okay. And so why would this be called a low pass filter? Well, it's because look, for all of the frequencies in this range, the magnitude of the frequency response is, sort of close to 1. Okay, again, this is such a simple circuit. There's only 2 elements, right? That we can't expect it to be ideal. Like an ideal low pass filter might be something that looks sort of like this. Right, so all the low frequencies just get passed through completely the same, magnitude 1, and all the high frequencies are completely rejected, completely killed, magnitude 0. Okay, but that's in an ideal situation. Here we have such a simple circuit, we can't expect that, but still the low frequencies are relatively high in the magnitude of frequency response, and the high frequencies, you can see, get relatively smaller. Okay, so this circuit generally is sort of letting these frequencies through and not letting the high frequencies through. So that's why it's called a low pass filter. So you can imagine an ideal high pass filter might look something like this. All the low frequencies are destroyed and the high frequencies are passed through. Okay, and we'll get to that in 1 second. But hopefully this makes sense now why this is called a low pass filter. Again, the point is that if I put a sinusoid in, like a cosine omega t plus phi, we saw in the last video, what I get out is a times the magnitude of h of omega cosine omega t plus phi plus the angle of h of omega. Okay, so if this h of omega here is like close to 0 for these frequencies, then that term right there would be close to 0. And that means this entire thing is almost 0, right? So that's why it's rejecting those frequencies. Versus here, if this magnitude was close to 1, then I would get a cosine omega t plus phi plus the phase. And you can see that this is the same as this, just off by a phase. In magnitude, it's still the same. That's why it's passing the lows. Okay, so hopefully these ideas are starting to connect. I'm gonna erase that because that was just to remind you of the last video. But anyway, that's why it's called a low pass filter. Okay. So if that was a low pass filter, oh, sorry, one more thing. Let's plot the angle real quick. We're not gonna do this all the time because most of the time people are more concerned with the magnitude of the frequency response because that has to do with whether the frequencies get through or not. The phase is important in a lot of applications, but at least for us, won't be as important. Okay, so what does this look like? Well, what's the inverse tangent look like, first of all? Well, it looks something like this. Okay, it's sort of like that. So if I have negative inverse tangent, it's just going to be that flipped, where I kind of have these asymptotes here at like pi over 2 and negative pi over 2. So it's going to look, again, not a big deal. If we get it exact, just sort of generally something like that. This is the angle of h of omega. Okay, I'll put it up here. All right. So that is the angle. All right. So if this was the low pass filter, let's look at what the high pass filter looks like. All right, so let's do that example. So this is going to now be a high pass filter. And the idea is the same. Now we are going to pass the high frequencies and attenuate or reject the low frequencies. Okay, so let's see what that would look like. And again, this is just one example. There are many ways to make high pass filters, and some of them can get very complicated depending on how much you want to control exactly what your filter does to your inputs. Okay, so some high pass filters have many, many components. We're just doing ones right now that are simple with just 2 components. Okay, so this is what we're looking at, and we're going to follow the same scenario. Okay, we're going to phasorize this because we want to look at the frequency response. We get 1 over j omega c. We get R. We get our input phasor. We get our output phasor. Same as before, it's just we flipped C and R, right? Up here it was R and C, and now we just switch them, C and R. Okay, so this is one example of a high pass filter, but we haven't shown why yet. So we got to find the frequency response. So the frequency response is h of omega. We know it's the output phasor divided by the input phasor. Okay, again, the output phasor, it's just a voltage divider. It'll be this impedance divided by the sum. So let's do that. It's going to be R over R plus 1 over j omega c. Again, the output phasor is that times VI, but then we're dividing by VI, so we can get rid of that. And again, I like to multiply this top and bottom by j omega c. I get j omega RC divided by 1 plus j omega RC. This times j omega c is 1, and then R times j omega c, j omega RC. Okay, so that's the frequency response. You can get that relatively quickly for such a simple circuit. Now let's look at the magnitude. Okay, again, the magnitude of the ratio of complex numbers is just the magnitude of the top divided by the magnitude of the bottom. Divided by the magnitude of the bottom. I'll write it like this once. Okay, now let's do that. So what's the magnitude of the top? Okay, well, we know that the magnitude of a product of complex numbers, is just the product of their magnitude. So this is equal to the magnitude of J times the magnitude of W times the magnitude of R times the magnitude of C. What's the magnitude of J? Well, J is just right here on the unit circle in the complex plane. So the magnitude of that is 1. Magnitude of omega, I think I might have said W as omega. Magnitude of omega is whatever it is, right? Omega could be positive or negative. So we have magnitude of omega, but then R and C, we already know are positive real numbers. So just times R times C. Okay, so I'll just say RC magnitude of omega. And the magnitude of the bottom is what we had before, the real part squared plus the imaginary part squared. Okay. So that is the magnitude of the frequency response. And let's draw that again. Okay, and I'm just going to draw it over here just because it's a rough estimate. Okay, so what does this look like? Omega and magnitude of h of omega. Well, when omega is 0 now, this 0 up top kills the whole thing. So the frequency response is going to start out at 0. What about when omega is really large, either really positive or really negative? Okay, well, again, this function is even. Okay, this amplitude of the frequency response is even in omega. Whether I plug in plus or minus omega, I get the same thing. Absolute value of plus or minus omega is the same thing. And here I'm going to get omega squared. So I get the same thing whether I plug in plus or minus omega. So when omega is, say, really large and positive, I'm going to get RC omega divided by the square root of 1 plus RC omega squared. Well, when omega gets really big, this 1 doesn't really matter. So I essentially have RC omega divided by the square root of RC omega squared. That's also just RC omega. So I get close to 1. And since the function's even, it's going to look like that going in the negative omega direction too. So, you can plot this somewhere, but I'll just tell you it generally looks something like this, just as a ballpark, where this is 1. Okay, so you can see that this is definitely, not our ideal version of a low pass or of a high pass filter. We would like something much better that was sort of like this. It passes the highs and it completely kills the lows, but we only have 2 components in our circuit, so we can't ask for that much. Okay, so this is what it looks like, but still you can see the low frequencies here, okay, are generally, getting attenuated. The magnitude of the frequency response is smaller, and the highs are generally getting passed more. Okay, just generally. Again, you can make much more complicated circuits to do things, more accurately. All right, and the angle, I'll just leave for you. You can think about that on your own. That's not as important for these filter examples to get across why they're called what they are. Okay, and one more thing before we move on to yet another type of filter is I just want to mention for practice, a good thing to do would be to try and make a low pass and a high pass filter, but instead of using a capacitor and a resistor, try to use an inductor and a resistor. Okay, so see if you can figure out how to combine an inductor and a resistor, nothing else in a circuit, just like this. Okay, here we used a capacitor and a resistor. Figure out how to combine an inductor and a resistor to get a high pass filter and a low pass filter. Okay, that would be good practice. Okay, and we can go over that in class too, if you get stuck. All right, so that was a low pass filter, that was a high pass filter. What about what else can we do? Well, there's something else called a band pass filter, sometimes called a BPF. Okay, and what does this do? Well, if an ideal low pass filter passes the lows and gets rid of the highs, and an ideal high pass filter passes the highs and gets rid of the lows, well, an ideal band pass filter would look something like this, where it just passes some frequency band, both in positive and negative frequencies, some frequency band, and it gets rid of the lows and it gets rid of the highs. Okay, so that would be an ideal band pass filter. Okay, and that's what we're going to look at right now. All right. So what does this look like? Well, again, just one example. And here we're going to use an inductor, a capacitor, and a resistor. Oops. So inductor, capacitor, and then a resistor. And we're going to have our input voltage and our output voltage. This is inductor, capacitor, resistor. All right, let's phasorize it, because we want to see what the frequency response looks like. So I'm going to get my inductor impedance, which is j omega L. I'm going to get my capacitor impedance, which is 1 over j omega C. And I'm going to get my resistor impedance, which is R. And then my output phasor and my input phasor. All right, so we phasorized it. Now we want to find, yet again, what the frequency response is. Okay, and we want to see if it looks anything like the picture we drew before, where it's passing a frequency band. That region of frequencies it passes is sometimes called a frequency band. The frequency response is what? Well, again, just a voltage divider, right? You can get by on a lot with that. Okay, so now it's going to be this impedance divided by the sum of all those impedances. Okay, so this is going to be that impedance R divided by R plus j omega L plus 1 over j omega C. And again, I just like to get rid of that 1 over j omega C. So I'm going to multiply top and bottom by j omega C. What do I get? I get j omega RC over this times j omega C gives me 1. This times j omega C, what does it give me? Well, the j's, I have j times j, that's negative 1. And then I have omega squared times LC, so LC omega squared. And then j omega C times R is j omega RC. And yet again, we're mostly interested here in the magnitude of the frequency response. Okay, because we're interested in this band passness of this filter. Okay, so we want to see how the magnitude of the frequency response is changing for different omega values and see if it's actually passing frequency bands and attenuating low frequencies and high frequencies, just passing within what we call these frequency bands, okay, somewhere in the middle range. And so how do we find the magnitude of the frequency response? Well, we've seen this a couple times now. Okay, so it's just going to be the magnitude of this thing, the frequency response, and that's the magnitude of the top divided by the magnitude of the bottom. So the magnitude of the top, what is it? Well, it's just the product of the magnitudes of each of those different numbers. And we saw this in the last example, that just gives us RC times the magnitude of omega. Okay, and then divided by magnitude of the bottom, which is just the square root of the real part, squared plus the imaginary part squared. Okay, so that's what we get. And I can let you think about, the angle of h of omega on your own if you'd like. For, the high pass, low pass, band pass qualities of these filters, like I said, we mainly just care about the magnitude. So I'm going to just look at that for now in this video. And so let's try and graph this. So what does this look like? Well, now when I plug in a very low value of omega, say omega equals 0, then the omega up here is going to make the numerator 0. The denominator is going to be 1, I guess. Okay, so that's going to be 0. So I know I'm equal to 0 when omega is 0. And then when omega is really large, okay, let's say if omega is really large and positive, down the top, I'm going to get something that looks sort of like omega. And on the bottom, I'm going to get something that looks sort of like the square root of what? Well, if omega is really large, here's an omega to the 4th, here's an omega squared. This term is going to dominate. So I'm going to get like the square root of omega to the 4th, which is just omega squared. Square root of omega to the 4th is omega squared. So I just get 1 over omega. And this was when omega was really big, either positive or negative, because again, this function is even. The magnitude of the frequency response is even because absolute value of omega, whether I plug in plus or minus omega, I get the same thing, and everything else has an omega squared. Okay, whether I plug in plus or minus omega, I get the same thing, so it's even. And so whether omega is really large or really small, it's going to fall off sort of like this. So I know I'm going to be going to 0 eventually. The only question is what happens in between. And you can try and analyze this more by hand, or you could just, put it in your favorite plotter. And it turns out it looks something like this. Okay, it kind of has these peaks. Okay, and again, this function's even, so it should look completely symmetric. The drawing isn't perfect. Okay, but it should be mirror symmetric across that vertical axis. And you can even find where these peaks are. Okay, again, you can try plotting this yourself, and it turns out that you get 1 over the square root of LC and negative 1 over the square root of LC. Okay, so the inductance times the capacitance, square root, 1 over that, plus or minus, that gives you where these peaks happen. And you can actually analyze that by hand. You can get that result by hand looking at this function, a series of steps. Okay, we can talk about it in class if you'd like. But for the purposes of this video, I think this is sufficient. And try out some values. You can plot this in maybe Desmos or something, and you can see how the magnitude of the frequency response changes based on R, L, and C. Okay, but the reason it's called a bandpass filter again is because sort of in this low frequency range, you can see the magnitude of the frequency response is, relatively small. It's kind of attenuating those frequencies in the low frequency range. In the high frequency range, it's also attenuating those frequencies. And it's just in this kind of middle band, this middle frequency band, where the frequency response is close to 1, okay, or at least larger than at the lows or at the highs, okay? And that's why it's called a band pass filter, because it's passing the frequencies in this range, and it's sort of getting rid of the frequencies that are low or high. Okay, so that's why it's called a band pass filter. And yeah, that's all I had for this video. Hopefully these 3 examples have given you a better feel for the frequency response and what these filters are all about. And again, adding more components to these filters can make them much more complicated. Maybe you want to have a filter where, maybe it looks something more like this, right? Maybe it's more localized around a frequency band that's smaller, right? Or maybe you want to, push this frequency band more to the higher frequencies, right? So all of those changes you can make either by changing the components you're using here, or by changing your circuit and adding more components to allow yourself to have greater control over exactly what your filter is doing. Okay, cool. So that's it for this video, and I will see you in the next one.